Yeah, good.
All right, thank you. All right. Good afternoon, everyone. My name is David, and I'll be presenting to you about my project with HIVE called Mars Craters Visualized Across Different Spectrums. To put it simply, it is just to come up with something that allows the users to look at different data domains of Mars in a really user-friendly platform. Now, before we start, let's have a look at some background about Mars. So it is the fourth planet from the Sun. It's one of the closest planets to Earth. And its radius is 53% of Earth. So it's quite small comparing to Earth. So you can see from this graph here. And Mars, over the past 45 years, has been surveyed in great detail, mainly because it is potentially habitable for human beings. Now, why do we look at craters? That's mainly because cratering is a geological process that's common to all planets. And we all know that craters are formed by the intense impact of the meteorite or the rocks and the crust. And there are a few craters here on Earth for scientists to study closely, so then we can apply for the same knowledge, put it on Mars craters, and to understand Mars craters or the entire Mars or the evolution of Mars better. And so any unusual formation of craters can indicate there's something unusual about the surface or some even internal changes of the planet. Now, people have developed some really good softwares to visualize Mars. This one on the left called JMars. It is a software that you need to download, and it has many data domains or data sets included in it, and it's very flexible. So you can, say, lay out two different data layers and then modify the transparency of one layer. Then you can see both layers at the same time, and you can see how they relate to each other. However, the only drawback with JMars is that it is very slow when it comes to loading up the images. So whenever you zoom in, zoom out, when you use your mouse to drag to another place, it has to reload everything again, and that can take a really long time. On the other hand, Google Mars is completely the opposite of what JMars can and cannot do. So Google Mars is just a website. You don't need to download that. And it can load up images very quickly. And it's really user-friendly as well. So you can easily navigate to different places of Mars. However, there are only 3 data sets or 3 data domains included in JMars. So then that means it's not fit for research purposes. It's only good for the public to get a brief understanding of how Mars looks like. So then that brings us to the objective of this project. It is to come up with a platform that can resolve these issues. So some requirements of the platform will be, number 1, it must be user-friendly and easy to use. Number 2, it should be interactive, meaning that you can jump onto different craters, looking at different data sets. And then you should load up the images pretty quickly, unlike JMars. And also you need to have the inclusion of many data domains, so that way researchers can look at this and know more about Mars craters. And last but not the least, we need to include all craters that were listed out at the start of the project by my supervisor, Katerina. Now, there are 7 data domains that were included inside this project, and they are Molar, which stands for Mars Orbital Laser Altimeter, and I'll go through the details of each data set later. And the second one, crustal thickness, that is the thickness of the crust on Mars, and free air gravity anomaly, Bouguer gravity anomaly, geological map, THEMIS, which stands for Thermal Emission Imaging System. Day means it was surveyed at daytime, night surveyed at nighttime. Now, there are also some unused data sets. They were suggested to be included at the start of the project, but due to their poor data coverage, we chose not to use them. So the first one, Omega, there are 5 data layers in that, and Omega mainly shows the chemical composition of Mars surface and also the dust cover. Now, Molar. So that is a global map of Molar. Different color represents different height at different places, and it has a pretty high resolution of 200 meters per pixel. And it shows the altitude of the Mars surface. Now, crustal thickness, like I explained, was just the thickness of the crust. Now, some gravity maps. So those two are both gravity maps, and they are in pretty low resolution. So the only difference between free air and Bouguer is that free air is corrected for only the height at which the gravity was measured, but Bouguer was corrected for the height and also the attraction of the terrain, say like a huge rocks that may somehow increase the gravity. And geological map. This map shows slightly more information than the others, and it has a slightly higher resolution than the gravity maps. So it shows, number one, the names of craters and the other terrains, and number two, it also shows the rough age of different areas of Mars. So you can see there are many different colors on this geological map, and different color represents different age of the surface. Now, Themis day and night. So Themis day and night, these two data sets are the highest resolution amongst all data domains, and they are at 100 meters per pixel. And they also have almost complete data coverage of the entire Mars, so which make them pretty good to work with. And also, so Themis are just pretty much images of the visible and infrared parts of the Mars surface, and that shows the thermal properties of the surface and the mineralogy of Mars. Sorry. And here it's a general workflow, or like how this project was done. So at the first, TIFF files were collected. So those were the global maps of Mars. And after some data manipulation done in ArcMap, it was then exported into PNG files, so like pictures. And then each picture is one layer for one crater. So they were cropped out as well. And also, after that, those PNG files were then imported onto Penotor Pro 2.5 for the construction of the final platform. And this is a screenshot for the finished work. And it is interactive, user-friendly, loading. It loads very quickly. And for each crater, there are 13 data layers. Now, I'll just talk about a few data manipulation that happened here in ArcMap. So number one, we need to reproject the craters. So, because we know that the entire data set came as a global map, and so it was using the projection of simple cylindrical, and that is the most common projection that we use for map projections. But the only problem with that is as you go to higher latitude, the images or the shapes are getting slightly distorted, and until at the south and the north pole, a single dot becomes a straight line. So these two images, they are so they show the same area of the same crater, but one was not projected correctly. This one was after correctly projecting it. So this reprojection was done in ArcMap as well, so that a circle looked like a circle. And then also another work is stretching the color ramp. So those two images, they are showing the same information about Mars. So they're all about crustal thickness of Mars, and they're all showing the same area. However, you can see to the left, that image is just kind of just green and yellow. You can't really see much from that. So then, because that is only a small part of the entire global map of crustal thickness. So then, because of the color ramp, it's only showing a small section of the color ramp of the entire Mars. So then, to show a better contrast, we need to somehow re-stretch the color ramp or fit a new color ramp onto that. And that was done in ArcMap as well. So after that, it shows a better contrast. It shows more details that we used to be very insignificant. And then this work is done for the Molar crustal thickness, free air, and Bouguer anomalies data sets. Now, here's a short video of the result. Let's have a look.
soundtrack there.
It was the satellite was calling.
Yeah, so that's it. But there are also some limitations on this project. So number one, the amount of data layers are only those that were chosen at the start of the project. So adding any new data layers means that we need to start from the start over again. So like we need to export the images from ArcMap and then export them as PNG files and then import that onto PanelTool Pro again to reconstruct the project. Number two, the number of craters are also limited to those that were chosen at the start of the project, and no detailed explanation of what there were no detailed explanation of what each data domain is. However, this was included in the report. Now, some future work that can be done. So, number one, definitely adding higher resolution data sets like HIVE and CTX. Some of those data sets have a resolution of about 5 meters per pixel. So comparing to Themis, 100 meters, that's much more detailed. And also we can try to include more craters. So now we only have 19 craters in total, but there are like millions of craters on Mars, so we can definitely add more craters in. And also we can try to reduce the size of the entire project or the entire platform that was built. Now the size of the outcome was 120 gigs, and you can't really put that onto the website because that takes just too much space. So we can try to reduce the size, and then we can possibly put it online for the public to see it. Now, at last, I'd like to thank Kurt and HIVE, Katerina, Anthony, and Wesley for their help and support. Thank you.